This is the first video about quantum mechanics. Now, quantum mechanics is very much a physical chemistry topic. It's very nitty-gritty, very nuts and bolts. What does an atom look like? Even more specifically, what do the electrons around the atom look like? Where are they? How do they arrange themselves? In a much greater detail than we've talked about before. Now, the first thing we need to focus on as we think about this is light. Most especially how light interacts with atoms. But before we can talk about how light interacts with atoms, we need to think about light in general. So, light, if you're an ancient Greek or you're Isaac Newton in the Middle Ages, to you, light is a wave. Here is a wave. A wave has certain properties. For example, the distance between the same part on two successive waves, usually the peak, but really it doesn't have to be. It could be from trow to trow or whatever. But anyway, this distance here is something called the wavelength. And it is a distance. It's measured in some sort of length unit, usually meters or nanometers or micrometers, some sort of meter unit. The symbol is a Greek letter, lambda. If you look in your computer, you type an L in symbol font, you will get that. And that's what it is, a Greek letter lambda. The other really important thing we want to worry about with a light wave is frequency. Frequency is another Greek letter for its symbol. It's kind of like this. It's called a nu, N-U. If you type an N in symbol font, that's what you'll get. Frequency is not speed, okay? It's a little different. The idea is frequency is if you're standing here, how many of these peaks go past you in a length of time. That's what frequency is. Think of yourself standing on the shore. How frequently the waves hit your feet. That is frequency. The unit of frequency is, in fact, waves per second. Lots of times people don't bother to write waves, so they will just say 1/seconds, or they will say seconds to the -1, which is all the same thing. And there is a name for this unit, which is Hertz, H-E-R-T-Z, abbreviation H-Z. All of these things are the same thing, and they are the unit of frequency. Now, wavelength and frequency are inversely proportional to each other. The way we say that is wavelength is proportional to 1/frequency. That's how you would write that in math. They are inversely proportional. As one goes up, the other goes down. But if you multiply them together, lambda times nu, you always get a constant. And that constant, symbolized by c, is in fact the speed of light. If you've ever heard of Einstein's famous E equals mc squared, that's the same c. Though that equation really has very little to do with what we're talking about. But it's the same c. It's the speed of light. In a vacuum, in metric units, light travels 3.00 times 10 to the 8th meters per second. Okay, 3 times 10 to the 8th meters per second. That is the speed of light in a vacuum. That's a constant. It's a constant of the universe. Light is always traveling at that speed. So if I ask you a question about a wavelength, about a wave, and I say to you, how fast is it going? That is always the answer. 3 times 10 to the 8th meters per second. Now, where does this come in the world? Well, if you think about visible light, all this light that we can see, here it is. Okay, this is what's called the electromagnetic spectrum. This axis here is wavelength in nanometers. So as the wavelength changes, the color of the light changes. How that light interacts with our eye, essentially, changes. So, if you heard of Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, this is Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. That's Roy G. Biv. But the electromagnetic spectrum isn't just visible light. When we talk about light, we don't mean just visible light. We actually mean all of this. Gamma rays, X-rays, ultraviolet rays, infrared rays, radar, FM radio, AM radio, television signals. All of those things are, in fact, simply different wavelengths of light, different frequency of light. It's all the same. It is simply those waves. It's simply a matter of whether we're talking about a wave like that or very close together like that. But all these rules apply to waves exactly the same way. So, knowing this equation, C equals lambda nu, I give you lambda, you can figure out a nu. I give you nu, you can figure out a lambda. Very simple. It's a simple, straightforward division. Nu equals C over lambda. Lambda equals C over nu, right? It's very easy to rearrange this into either of those guys depending on what you need. So, for example, I say to you, I have a laser which is 1064 micrometers, and you want to know, that would of course be wavelength because it's a meter unit. You want to know the frequency. You say, okay, the speed of light is 3 times 10 to the 8th meters per second, so I got to convert that guy into meters. So 1064 micrometers. You might want to brush up on your metric conversions. 10 to the 6th micrometers in a meter. That gives me 1064 times 10 to the negative 6, or 1.064 times 10 to the negative 3rd meters. And then that's the wavelength in meters. Now I know that nu is 3 times 10 to the 8th over 1.064 times 10 to the minus 3rd. Plug that into my calculator, and I get 2.82 times 10 to the 11th, and this is frequency, so my unit is hertz. And that's all it is. It's a plug and chug. No matter what I give you, frequency or wavelength, you simply use C equals lambda nu and solve it. And that's beautiful, and it works gorgeous. The problem is, light is a complex thing. If you think about a prism, Isaac Newton, in fact, did a lot of work with prisms. That's the kind of thing. Right, it's a little piece of glass. You show the, you shine the white light on it, and you get a rainbow coming out. All the light diffuses, spits out. You get a color, something like that. Because the prism interacts with all those waves and splits them apart and makes them easier to see. And that's very typical wave behavior. So light is a wave. There are other ways we know light's a wave. Young's double slit experiment is another way we know light is a wave. The idea there is you have a light source and you shine it at basically two holes. And what you don't see is a light here and a light here. Even though you think that's what you would see, the light would go through and make a spot there. The light would go through there and make a spot there, and that's what you would see. But it isn't what you see. What you see in real life is this. You see an alternating band of light and dark. And it's because of this idea of interference of waves. So here are the waves coming through the single slit, but when they go through a double slit, the waves that are going through this slit and the waves that are going through this interact with each other. So some of them add up and make bigger waves, i.e. lighter areas, and some of them interfere with each other. The top part of one wave cancels out with the bottom part of another wave, and that's where the dark areas come from, and you end up with alternating bands of light and dark. That's another way to say, oh, look, light's a wave. Which, if we could explain all experiments that way, it would be fabulous. Unfortunately, we can't. The most famous experiment that does not actually work with a wave equation is something called the photoelectric effect. Now, Einstein won the Nobel Prize for explaining the photoelectric effect, which tells you how much this was bothering people. Everybody always thinks Einstein won it for E equals mc squared, but he didn't do it. He didn't. He won it for the photoelectric effect. The thing about the photoelectric effect was it was bothering people a lot. It was like the one thing they couldn't explain about light, saying light was a wave. The idea was that if you shone light on a piece of metal, you could get electrons to come off the metal. And you can measure that by, for example, detecting a current, because that's what a current is. It's moving electrons. The problem is that only works above a certain frequency. Okay? You needed a high enough energy coming in before the electrons ejected out. And that doesn't fit with wave theory. Okay? Here's why that doesn't fit with wave theory. Because wave theory says waves add. If I have this guy and this guy, they add up and make an even bigger wave like that. So if I have a wave of a certain energy, the more I shine this wave, the more I'll get more and more giant peaks here, and eventually I should get enough energy to kick out these electrons. But it doesn't work. I can shine this light all day long and no electrons will come out. I have to have a light of a high enough frequency, a high enough energy in order for the electrons to come out. And there was no way to explain it. So the only way to really explain photoelectric effect is to say light isn't a wave at all. Light is a particle. And a particle of light we call a quantum of light. Plural quanta. And we say light is quantized. It comes in particles. But, you say, what about all those other experiments where light was acting like a wave? Absolutely. Hence the problem. We have to say somehow light is both a particle and a wave. Light is both a particle and a wave. This is called wave-particle duality. It is both. In some way we really don't understand. And it's not like the photons come out in this wave pattern. That's not right. Okay? It is somehow in ways we can understand, both a particle and a wave, and we simply force it to act like one or the other in each of these different experiments. Which brings us to Niels Bohr. And finally, we're going to bring atoms into this discussion. Now, Niels Bohr is working with the Rutherford model of the atom. He's got some sort of nucleus, and essentially he knows out here somewhere there's some electrons. What he's trying to explain is something called absorption spectroscopy. What he's trying to explain is this. Remember that lovely prism that gives me all the wavelengths of light? Atoms don't do that. They give me only certain specific frequencies. Hydrogen only gives me these. If I shine light on hydrogen, I only get these frequencies back. This one's mercury. This one's neon. It's consistent every time for the same element, but I get these totally different spectra for different elements. And that's what Niels Bohr is trying to explain. So he thinks about this idea of light being quantized. And he says, I'll bet electrons are quantized. He says, I'll bet around this nucleus we have certain orbits an electron can be in. It can be here. It can be here. It can't be anywhere in between. Now, this is a pretty radical idea, that we have this idea that an electron can be here, an electron can be here, an electron can be in another ring, but it can't anywhere in between. Think about a ladder. You're climbing a ladder. Your foot can be on the first rung, your foot can be on the second rung. It can't ever be between the rungs. And that's what Niels Bohr is saying about these electrons. There's certain places they can be. So when I shine light, for example, the electron gets excited, jumps up to a new rung of the ladder, falls back down again, giving off the light. That's a shorthand for light. Giving off the light that got shown on it. And that's where the spectrum is coming from. All of these bands represent energy differences between these rings, these orbits of electrons. And he has really no theoretical underpinnings to say this. He merely says, I'm trying to explain experimental results. The theory actually comes later. Now, this idea of energy being quantized leads us to another formula. E equals h nu. This is the same nu that we were talking about before. It's frequency. This E stands for energy. H is something called Planck's constant. That's named after a German scientist named Max Planck. Planck's constant. And the value of Planck's constant is 6.626 times 10 to the negative 34th joules times seconds. Yes, that's times. It's not per. We're used to seeing a per there, but it's times. Joules times seconds. Because frequency is in per second, and the seconds have to cancel and leave you with joules, because that's a unit of energy. Joules. That's the unit of energy. And again, in practice, this guy's a plug and chug. I give you, you know that's a constant. So I give you either energy or frequency. You solve for the other one. And of course, by combining E equals h nu and C equals lambda nu, I can go from energy to wavelength also. All right, I think that's enough for our first video.